Okay, so 60 centimeter, 200 gram beam, that's what we've been using. It's like 193, 194 grams. We'll round it off. Okay, rotating as we've seen it rotate. What's its moment of inertia? We've actually calculated, I hope you've estimated it, calculated it based on what you observed in lab, dropping the magnets on it. Let's see what it really ought to be. We've got 4 minutes, we can do that. Well, we probably can't. We'll just take the first step. Then I'll tell you where it goes. And then I'll let you do the interval, okay? So, mass per unit length. If we want it exact, we'd use 10/3 gram per centimeter, but we'll just use the decimal. We'll probably just round that off to 3.3 grams per centimeter just for simplicity, okay? Although 10/3 is not a difficult quantity to deal with. So here we have it. And here we have the axis of rotation, okay? Now my question is, how much mass of that beam is located between distances located between 15 centimeters and 16 centimeters from the axis? You should be able to tell me pretty quickly.
3.3 grams per centimeter.
Huh?
3.3 grams, yeah.
Three? You're still saying 3.3 grams?
Yes.
I don't think you've got it all.
Sorry.
I'm sorry?
Just looking at King. Length.
What's wrong with 3.3 grams? It's a 1 centimeter.
That only calculates half of the mass because it's on each side of
Yeah, you got, okay, so 15 centimeters here, and 15 and 16 here, right? So you got 1 centimeter. Mass about 6.7 grams, right? Okay, so what's the kinetic energy? Kinetic energy of that segment, right? Of those segments. I mean, if you want to use a specific omega, you could, but you don't need to because it's not going to. Well, the kinetic energy is what? Go ahead.
1/2 omega times 6.7. Wait. Hey. Omega times.
Got a length of it as well.
Can you read that? I'm too close. I can hardly make it out for the roughness of the board, but there it is, okay? Now what I use 15.5 centimeters times omega?
Because we want to look at the point, the mean point at that.
Yeah, well, that's my best approximation. It's not really my best approximation, okay? Since the speed of a particle is proportional to the distance, but the kinetic energy to the square of the speed, you don't really have quite a linear relationship, so using the midpoint isn't exactly right, okay? But it's very close because you've only got a 1 centimeter, you've only got a 6% difference in the distance from one end of from one radius to the other, okay? And that equals one half I times for the segments, times the omega squared, right? Well, you look what happens to omega. Squared here, it's squared here, it doesn't matter what omega is, as we saw last time when we did the problems, okay? So I'll let you finish that. Now we could do that for every 1 centimeter increment, right? And add them all up. Would we have the exact moment of inertia? Would we be close? We'd be very close. Okay? Would we have an overestimate or an underestimate? You can think about that. Well, problems I'm going to assign include an analysis like that, but I don't ask you to do it for 1 centimeter increments. I ask you to do it for 10 centimeter increments. There are only 3 of them. You're not going to get a real good result, but it won't be that totally off the wall either. Okay?